Okay, let's do some math for fun. In this video, we'll be doing 10 rounds of integral battles in one take. I know, I'm sorry, it's not 100, but this is going to be really fun because we will be battling between elementary integrals versus non-elementary ones. And for the non-elementary ones, you guys should just think about them as the ones that have no answers for our Cal 1 and Cal 2 classes. Later on, you can actually use special functions to answer them, but again, for now, just no answers, right? And the point of doing so is that, well, here's an example. Sometimes when we are doing integrals, one integral might look so similar than the other, but unfortunately, maybe one has the answer, it might be just hard, and the other one, in fact, it looks hard, and the worst thing is that it has no answer. And it's a good idea to know some of the famous ones that they have no answers, so that we don't bother to solve them, right? So that's the idea. Anyway, you guys can also go download the file in the description, right? And here we go. Let's look at the first one. Integral of cosine of x squared versus the integral of cosine of ln x. Well, take a look right here. As we all know, x squared is easier than ln x. So, isn't it? This one has the answer, this one has not. The truth is, that's not true. The truth is, this one right here is in fact, the one has no answer. This one has the answer. And here we go. We will be doing the integral of cosine of ln x. And this right here is going to be good for your Cal 2 class. We'll be using the techniques mainly from Cal 2, such as integration by parts, trig sub, partial fractions, and whatever we need, right? Anyway, here we go. Let's look at the integral of cosine of ln x. Well, we know how to differentiate cosine of ln x. And when we differentiate, we will have to use the chain rule multiplied by the derivative of ln x, which is 1 over x. And we will have to integrate 1. And that's x. That's a good idea. Let's try to do this as integration by parts so that I can differentiate this and integrate the other one, right? So here we go. Let me put this down right here for you guys. Let me put down d and then I. You guys will see why I want to put it down right here. Anyway, to get ready, put down the plus minus, and we will be differentiating cosine of ln x, and we will be integrating 1. Integrating 1 just x, and differentiating this, the derivative of cosine is negative sine, and the input stays the same, and the derivative of ln x is 1 over x, so multiplied by that, which is like this, right? Remember the chain rule. All right, now, as we all know, this times this is going to be the first part of the answer. That's great. So this is equal to this times that, which is x times cosine of ln x. And when we multiply this row, remember we have to do this. This row will still give you an integral. Be careful with the sign though. You see, we have minus and another one. So negative times negative, we get positive. So here we have a positive integral. So plus integral. And of course, we see that this is over x and this is multiplied by x. So they cancel out. That's really nice. And we just have this, namely sine of natural log of x. So let's put that down right here. And notice this integral is very similar with the original. So let's try to do integration by parts again. And of course, we'll do the DI format. So here we have to start with another D and I, plus minus. And we are going to put this to be differentiated. So sine of ln x goes here, and we will be integrating 1. When we integrate 1, we get x. When we differentiate this, the derivative of sine is cosine, and we keep the inside. And the derivative of ln x is over x. Again, chain rule. Now, we are going to multiply this and that. So that will give us the first part of the answer. And that will be this part, right? So keep that in mind. So let me just put this down in blue. This is going to give us this times that, which is x times sine of ln x. And we still have to multiply this row and put this in an integral. Again, x and x cancel out. That's very nice. Well, in this case, we have a minus integral, so this is going to be a minus, and let me just put this down in red, minus integral. And we have just this, namely cosine of ln x dx, just like that. Well, good thing is that we just have a plus in the front, so plus parentheses that we don't have to change any signs, so that's good. And now have a look. On the left-hand side, we have the integral of cosine of ln x. This is the first part of the answer. This is the second part of the answer. And we have a minus integral of the same thing. That's really nice. This is what we can do. We can just bring this to the other side and then clean the coefficient. That's all we have. So let me show you. So let me just copy this down again. We see that we have this equals x times cosine of ln x plus this blue part from here. And now, as we mentioned it, we are going to add this integral on both sides so that this will be gone. And here we do the same thing, of course, cosine ln x in the integral. And here we go. We have one integral in black, one integral in red. Altogether, we have two integrals. And we have the cosine of ln x dx. First part, second part of the answer. X times cosine of ln x plus x times sine of ln x. But don't put on the plus c yet. This is not the final answer because we have to get rid of this 2. And to do so, we can just multiply everybody by 1/2. So that's it. In the end, let me just write down the answer nicely for you guys. We will have the integral of cosine of natural log of x dx being equal to 1/2 times x cosine of ln x plus 1/2 x times sine of ln x. And we are all done. Don't forget the plus c. So as you can see, this right here is actually doable because we just did it. This is the answer. On the contrary, even though this looks easier, but no matter what we do, unless we use special function, otherwise we don't have an answer for that. So very cool, and we have 9 more to go, right? So keep that in mind. So right now, what you guys can do is, while I erase the board, just take a look at the second question and think about which one is doable and which one is not. Just take a guess. And for each question, I set it up as one is doable, the other one is not. So maybe if you don't want to guess, then you can just try to solve one of them. If you can solve it, that's good. And that will mean that the other one is not doable. And after all this, hopefully you will have a better idea and you will be more aware of the integrals that are not doable. Okay, so here we go, number 2. We have the integral of ln of 1 minus x squared. Okay, we see the x squared again. Man, I don't know. It kind of disappointed us earlier. But anyway, versus the other one, the integral of ln 1. But this time we will have minus e to the x dx. The truth is, this one is not doable because we can totally do that one. Let me show you. Again, we'll be using integration by parts. So here we go. Let me just write down this integral again. So here we go. And I will put down the d and I right here. This is all I need, okay? So the space right here, d and then the I. Here we'll be differentiating this again. So we will have ln of 1 minus x squared. And don't forget the plus minus to get ready. And integrate 1. Integrating 1, we get x. Differentiate ln, we get this in the denominator. So we have 1 over 1 minus x squared. But don't forget the chain rule, multiply by the derivative inside. The derivative of 1 minus x squared is negative 2x. So that's what we have. Now, this times this is the first part of the answer. So we have x times that, x ln of 1 minus x squared. And we are going to multiply by this row. Don't forget to put this in the integral though. And minus times minus is giving us a positive, so plus integral. Check this out. We have 2x times x, so that's 2x squared. Let's put that on the top. And we have over 1 minus x squared on the bottom. And now, as you can see, we have a rational function right here. And to integrate this, it's actually not that bad at all because the degree on the top is the same as the degree on the bottom. We are just going to do long division first. So let's do that real quick. And perhaps I will do the long division right here. Why not? I will put this down. 2x squared inside. And let me write negative x squared right here first. Plus 1. Right? Keeping this order. Highest power go first. Anyway, when we divide, let's see, we need a negative 2. Negative 2 times this is positive 2x squared. Negative 2 times this is minus 2. And don't forget, when we do long division, we subtract. And when we subtract, this is gone, and 0 minus minus becomes plus 2, like that. In another word, we have to look at this integral as this. We have to add the integral. This is minus 2. This is the quotient. And this right here is still a fraction part. Okay, so we have the plus 2 over, and let me just write it back as 1 minus x squared, like this. Right, so that's the idea. And we have the dx. Again, long division, when the degree on the top and the degree on the bottom are the same, or maybe the degree on the top is higher, do long division, that's the deal. This right here, it's going to be really easy. This right here, we will have to do partial fraction for that. So have a look here. And perhaps, let me just do this way. Let me just kind of write the negative 2 right here and close this integral and plus another integral. So we'll focus on this integral right here only. To integrate this, we will have to factor the bottom. And when we factor that, we get 1 minus x times 1 plus x. And let's focus on this part. We are going to add the integral. This part is going to be broken down into 2, okay? So for the first part, we are going to have some number over 1 minus x. And the other one, we are going to have another number over 1 plus x. And here we'll be doing the cover up method. To figure out this number, we go back to the original and cover up the same exact denominator. Well, we also have to ask ourselves, how can we make 1 minus x equal to 0? And the answer is that x has to be equal to 1. And now put this 1 into this x. On the bottom, we will have 1 plus 1, which is 2. On the top, we also have 2. So 2 divided by 2 is 1. So this is going to be 1. Here, do the same thing. Well, how can we make 1 plus x equal to 0? X has to be negative 1. Put negative 1 in here. 1 minus negative 1 is again 2. 2 over 2 is 1. So we have another 1 here. So that's the beauty. And now, as you can see, we just have these people to work out. That's all. So perhaps let's just put on the answer for this. Integrating negative 2 dx is just negative 2x. Yeah? And remember, we still have this right here. So perhaps I'll just drag it down. So we have x ln of 1 minus x squared. This is this part. We have 2 more integrals to go. So here we go. Right. So again, just drag it down. Here. Write this down again. X times ln of 1 minus x squared, and this is minus 2x. Integrating this, check this out. We have a linear function in the denominator, right? So we will just get natural log, absolute value of the denominator, which is 1 minus x. And the derivative of 1 minus x is what? Negative 1. So we have to divide it by negative 1. So we have the negative right here, all right? Again, here is the deal. When we integrate 1 over ax plus b, this right here, it's a linear function in the denominator, and on the top we just have 1. The answer to this is natural log of the denominator in the absolute value, of course. Let me write it down better. Natural log absolute value ax plus b, and because the derivative of ax plus b is a, when we do the antiderivative, we divide the derivative if the derivative is just a number. So we can just put down 1 over a like that. And you can just do a little use up on your own to verify this, but you can also remember this. This only works if the denominator is a linear function, okay? And just divide it by the derivative for that. Don't forget to do this. Integrating 1 over 1 plus x. Well, this case we just have the plus and natural log of the absolute value of 1 plus x. The derivative of 1 plus x is just 1 divided by 1, doesn't matter. So this is it. Done. Plus c, right? We're all done for that. Okay, so here is the deal, right? Very interesting formula. Very interesting formula. Anyway, number 2, right? So this one is actually doable. This one is not. So, give x squared a chance. Even though the first one, it didn't happen, but, it takes experience, takes time to actually get familiar with all the integrals and all that. And of course, I came up with all these questions myself. So that's how it seems like, oh, I know everything, but, I prepare a lot. If you are willing to put in the time, you will know a lot of things too. So that's the deal, right? All right, for the next one, are you guys ready? Let's pause the video to look at it first, right? Look at it first and just try to think about it. It's much more fun to do the questions on your own, right? Not just look at me do the question. Anyway, here we go, number 3. It's a crazy one. The battle being between the integral of x to the x over, oh my god, man, dx versus the integral of x to the x power dx. Both of them look so intimidating, man. But the truth is, this one has the answer. This one does not. Keep this in mind. Sometimes when we are doing integrals, maybe the more, it's actually better, right? So keep that in mind. This right here, it's a really famous one. It doesn't have answer. Just cross it out, right? So if people ask you to integrate x to the x, just tell them that it has no answer. For now, just walk away. You can use power series for this, but that's later on. You can use some special functions if you want to, but again, later on. Check this out. How can we integrate this though? Well, in this case, when we have base x, we don't like that. We like to work with base e in calculus. So here is the deal. Still have an integral, but let's look at the x as the follow. E, right? We like to have base e for the base. How can we get the x though? Well, we know if we take e raised to the ln x power, this is still x because e and ln cancel, so that's good. And don't forget we still have that power, so we have to put this raised to the x over ln x power. And now check this out. When we have e to this power to that power, what do we do with the powers? Yes, we just multiply the powers. So in other words, we see this is the integral of e, and we multiply ln x times this x over ln x power. And of course, the ln x cancel each other out. In another word, this is just e to the x power, like this. Very, very good. Simple. This is like the simple one. Everybody's favorite. And when you integrate e to the x, of course, you just get e to the x. If you're done, you can put on plus c. But you know what's better is, look at e to the x. This right here is just the same as e to the x. So this is nicely equal to x to the x over ln x power, and then put plus c. That's it. Right? So here's the deal. If you would like, you can just write down the integral of x to the x over ln x power dx. You can just put this down as x to the x over ln x power plus c. Very, very cool, right? But that's the secret behind it. This is nicely equal to itself because this is just e to the x itself. Anyway, that's it. Haha. Now, let's look at number 4. Wow. Be careful with this one. We have the integral of x times the square root of x to the third power plus 4 dx versus the other one is the integral, and we have x times the square root of x to the fourth power plus 4 dx. X to the third power is lower power, maybe it's easier. But no, this one has no answer. You can try u sub, you can try trig sub, you can try whatever you would like. However, no matter what we do, we just cannot get this done. But this right here, we can just do some u sub and also trig sub, and you'll see how we can finish this, right? So here we go. Have a look right here. Let's look at the integral of x times the square root of x to the fourth power plus 4 dx. Well, first step, we are going to look at x to the fourth power x squared to the second power, and the reason is because we have this x in the front. The truth is, if we didn't have this x, in fact, the integral of square root of x to the fourth power plus 4 is also not doable. But since we have this x, it's actually possible, okay? So let's do the following. I will just write this down right here. This is equal to the integral of x times the square root of, here we have x squared, and we raise that to the second power plus 4 dx. From here, we take a u sub first. Let u equal to x squared, and du is just 2x dx. Divide both sides by 2x, so we can get the dx by itself, and we get dx equals du over 2x. And now, put everything back here, so we get this is equal to the integral of x times the square root. Here we get u, and we raise that to the second power, and then plus 4. And the dx is just nicely equal to du over 2x. Very, very nice. And now, of course, the x cancel each other out. Remember, x is not invited in the u world, but this is good because it's gone. But we have to integrate u squared plus 4. We have to do trig sub. It's okay, it's not that bad, okay? So let me just write this down. Here we have u squared plus 4, and for this 4, we are going to look at it as 2 squared, right? So just kind of remember, this is the form that we want to look at, and also we have the 1 over 2, so we can put that all the way in the front of the integration. So let me write it down here, and then we have the du right here. Now, trig sub in action. When we have a sum of 2 squares, we are going to use what? Tangent. Good. So here's the deal. We will let u equal to a tangent theta, and the a right here is this 2, right? So we will have to put 2 tangent theta and differentiate both sides. We get du equals to the derivative of this is secant squared theta d theta, and we get the du already, right? So we can just put everything into the u world. Check this out. U is 2 tangent theta, so we have this. I will put this down in what color? I don't know. Here we go. We have 1/2 and the square root, integral of the square root. U is this, so I will put a parentheses and I will get the, I'll just put this in blue. 2 tangent theta, square that, and plus 2 square. And we have the du. And now, just work this out. This is 4 square, 2 square, which is 4. So we have 4 tangent square theta plus 4. And we can factor out the 4, right? So we have the 4 parentheses tangent square theta plus 1. And the deal is that tangent square theta plus 1 is what? Nicely equal to secant square theta. So this is just 4 times secant square theta. And you take the square root. Don't forget we still have the square roots, right? Don't forget this guy. Here's the square root, here's the square root, here's the square root. So this is just a simplification. And now, let's see. We will have the integral. Well, of course, we'll have the 1/2 of the way in the front. Square root of 4 is 2. So this right here is another 2. So can we see? I think, yeah, 2. And the good thing is that squared and square root cancel each other out. I know we should technically put the absolute value, but for integration purpose, don't worry about it. Just, unless we have like limits of integrations. But for now, just don't worry about that. Right? So this becomes a 2 right here. Right? Square root of 4, of course. Anyway, this 2 can be brought to the front. So we have this right here. And we have the integral. And we just have, oh, I forgot the du. Du is 2 secant. Yeah. So anyway, this part is the du. sorry, du is right here. Du is all this, so we multiply by 2 secant square theta d theta, right? So I have to go to the theta world, like all the way. And that was just a simplification. Again, 1/2 right here. This 2 right here. And we have another 2. Perhaps I'll also put this down right here, just for fun. I will put this 2 in red, right? So we have that 2. And I have this 2 in blue. So I will put this down right here. We're good, yeah? Okay. Now, for this part, we have the square root and square cancel already. So we just have secant to the first power. So inside we have secant here, theta, but we have 2 more. So let's go ahead and multiply by secant square theta. And of course, we are in the theta world. So let's put down d theta right there. And let me just double check, because I remember when I was doing my 100 integral video and I messed up the 2 somewhere, like 2 or 3 times. So let me just double check. 1/2, it was the dx. So we have that red 1/2. And this 2 in red is just square root of 4, which is just a simplification. So that right there. And this is because of the substitution. So I think we are good this time. And I'm not going to cancel them out. If you know the reference, let me know. Anyway, we will cancel things out, but not all. That's what I was trying to say. Anyway, here we go. This right here, we have this 2 in blue. Why not? Let's put it down in blue. And we have the integral of this is just secant to the third power theta, d theta for that. Well, we do know what the integral of secant to the third power theta is. You guys can check my other video for that. But I will just tell you guys what the answer is, okay, for this video. So we have the 2 in the front, parentheses. If you work this out, you will get 1/2 natural log of secant theta plus tangent theta, and you add it with 1/2 secant theta times tangent theta, like this. Right? This right here is the answer for that part. And of course, we can distribute the 2. So the 2 and 1/2 will cancel. That's good. Now, we have to get back to the x world. First thing first, we will have natural log absolute value. This is secant theta. Theta is, man, we have to do some more work for that. Secant theta, we cannot just pick it out, huh? So too bad. So perhaps not now. All right, so this is how we get back to the theta world. Go back to the u world first. Actually, let's do both of them at the same time. We know this right here, u squared, u is equal to 2 tangent theta, yeah? So in other words, we know tangent theta is equal to u divided by 2. That's good. But we also know u was equal to x squared. So this is just equal to x squared over 2. Very nice. Now, based on this right here, tangent theta is equal to x squared over 2. We can draw a right triangle like this. Put the right angle here, which is theta, and we know tangent is equal to what? Opposite over adjacent. So in this case, the opposite is x squared, and the adjacent is 2. So we have the 2 right here. And now the beauty is that the hypotenuse is just the square root of this square plus that square. So I will just put this down for you guys. Name the parentheses x squared, but you square that and you add it with 2, and you square that like this. And of course, this is nicely equal to x to the 4th power plus 4 inside. Yes, it is the original square root. Huh. Anyway, here we go. 2 times 1/2, gone, right? And we have just natural log, absolute value. Okay, secant theta, let me put this down in red. Secant from a right triangle is hypotenuse over adjacent, so this over that. So we get square root of x to the 4th power plus 4 over 2. And we add this with tangent theta, which is just x squared over 2, so that's good. And notice, this is always positive, likewise for that. In fact, we don't need the absolute value, so we can just put on parentheses. And for this part, we just put on plus 1/2, and the secant theta, well actually no, 2 times 1/2 is just gone. Secant theta is just this over that, so we have the square root of x to the 4th power plus 4 over 2, and we multiply this by tangent theta, which is just x squared over 2, like this. So that's what we have. Now, here is the deal. Of course, we can put them together and over 2. And by one of the log property, we can do this. When we put them together, we end up with the natural log of square root of x to the 4th power plus 4, and then add the x squared outside all over 4. And then we know we can just have the top and also the bottom in 2 separate logarithms. So we get natural log of square root of x to the 4th power plus 4 plus x squared, and then minus, right, natural log of 2, like this, right? So that's good. And of course, we can just put this down, and perhaps we'll write this down as plus. Here times this is just x squared over 4, so it's 1 over 4, x squared, and we have the square root of x to the 4th power plus 4, like this. So technically, this is it. But here's the deal. We have to put down the plus c. Don't forget about that, of course. So let me just put it on plus c1 like this. And the reason is because in many situations, if you are checking the answer in the back of the book or maybe on Wolfram Alpha, because this right here is a constant, it's just natural log of 2. And this right here is also another constant. We can combine the constants together. A constant minus a constant is a constant plus another constant is another constant. So in the end, we just have natural log parentheses square root of x to the 4th power plus 4 plus x squared. Together, we label that as C2. But let me write this down first, which is plus 1 over 4 x to the 2nd power square root of x to the 4th power plus 4, in the end, plus C2, like this. And if you're presenting this for your answer, you can just say plus C. Nobody will get mad at you. So that's it, right? This is the answer for that. And hopefully, I did not make any mistakes for this one because, again, I make the mistake when I was doing the 100 integrals. So have a look here. All right, now continue. Can we do this one easily? I don't think so. Can we do this one easily? Yes, in fact, very easy, because if we let u equal to natural log of x, we just get 1 over x. So we get this done right away. And as I said, one will be elementary, the other one is not. So if we can do this one nicely and easily, that means the other one will have no answer. So this one is the one that has answered nicely, okay? So here we go. Integral ln x over x dx. Just do a u sub real quick. Let u equal to ln x. Du is equal to 1 over x dx. Perhaps isolate the dx, so we get dx equals, multiply the x on both sides, x du. So we get this as the integral ln x is the u over this x, but the dx is x du. So we get x du here. That's very nice because the x will cancel each other out. So now we have the integral of u du. And now we can, of course, just add 1 to the power, which is going to be 2 divided by the power. So we get 1/2 u squared. And let me just write this down first. And we get 1/2 parentheses. We can put down u equals the natural log of x. So let me just write that down. And we are done. Of course, don't forget the plus c. This is it. Right? So that's good. So move on to number 6. But this one should be pretty easy to see. This is really intimidating. Yes, I know. But that's not how you judge the integral, okay? You cannot judge the integral by its look. But we know how to deal with this because this right here, for the square root, we can just look at it as 1/2 power. So in this case, this is actually not doable. This is, and let's see how to do it. Here we go. Let me just write down the integral that we are doing. Square root of x, square root of x dx. First thing first, this is equal to, well, when we have this square root, we can look at that as the 1/2 power. So we have the integral, parentheses to the 1/2 power, and we have this x inside. But we have another square root, which is this one right here. It's okay, we can look at that as the 1/2 power as well. So we multiply by x, and we have another 1/2 power like that. And of course, we have the dx. Now, this is really nice because when you have a product like this, you can just have the following. This is going to be x to the 1/2 power, and then you multiply by x. 1/2 to the 1/2 power like this, right? X to 1/2 to the 1/2. Just multiply the powers, and we get 1/4. And let's do this in our head. 1/2 plus 1/4 is equal to what? 3/4, right? Write it down backwards. Anyway, this is pretty much all we need because, of course, we can just do the reversed power rule. Let's add 1 to the power. And 3/4 plus 1 is going to be 7/4, I believe. And then divided by the new power, which is multiplying by 4/7. Like that. In the end, the answer is just nicely equal to 4/7x to the 7/4 power. You don't need to write down anything fancy. You don't need a radical, whatever. I think this right here is enough. Put down the plus c. That's it. Right? Next one. You guys will like it a lot. So notice, here we have the square root of x inside of the sign. This right here is sin x inside of the square root. In fact, you know what? I'm going to put down number 8 side by side with you guys. What do you guys think? Which one is doable? If you say this one is doable, then I'm sorry. This one is actually not doable. Square root of sin x. No answer for that. Yeah, unless we use as special functions, but that's not what we're doing here. Well, in the meantime, because we are putting down tangent instead of the square root, maybe once we know this right here is also not doable. But that's not true. This is what's so annoying about integrals sometimes. The idea is that, in fact, this right here is just really, really hard. You will see. This is not doable. Yeah. So, here's the deal. We are going to do number 7 right here, just this, and then later on for number 8, we will do just that, right? Okay, so here we go. In fact, this one looks like the one that we did for question number 1. So you may want to just go into DI method right away, but it will be actually easier if we do a u sub first. So let me show you. I'm going to take u to be square root of x, and then square both sides first. That's easier to get a dx in terms of u, okay? When we do that, we get x equals u squared and differentiate both sides. We get dx equals 2u du. See, told you. So you see, we can just take this to the u world. We get the integral, and here we have the sign, and the square root of x is du. So let's put that inside, and the dx is just 2u du. So for this part, I will put down the 2u here, and then the du here. Because whenever we have this kind of integrals, we can just do it by integration by parts. Of course, we'll use the ds setup. And let me write this down right here. Let's put down the d and then I right here. D and then so the I. And don't forget the signs, plus, minus to get ready. In this situation, we are going to differentiate 2u, and we are going to integrate sin u. Well, integrating sin u, we get negative cosine u. Differentiating 2u, we get 2. Well, in this case, do we have a hope to get 0 in the d column? Yes, we do. So, plus, minus, plus. Don't forget the signs alternates. Differentiating 2, we get 0. Integrating negative cosine u, we get, well, the integral of cosine is positive sine. So we still get sine here, but maintain the minus here. The integral of negative cosine u is negative sine u, like this. Now, this is really nice because when we multiply the diagonals, they will give us the answers. For the last row, 0 times this is just 0, so it doesn't really matter. Okay, so we can come back here. Here we go. We get this times that, which is 2u times this, which is negative. So negative 2u, and we have the cosine u. And then next, we have this times that, negative times negative, so we have plus 2. And we have the sine u. like that. That's all we have, right? Yeah. And of course, in the end, whenever we see the u, we just replace that with square root of x. That's all. So here we go. This is going to be negative 2 square root of x, and we have cosine of square root of x, and plus 2 sine of square root of x. And that's it. In the end, don't forget the plus c. Of course. Very, very nice. Yeah. If you guys would like to help me translate to different languages, I can do that, right? Just help me and I'll appreciate that. And I'll make into shirts too. Yes. Anyway, this right here is it. I was about to say, let me know if you guys have any questions, but I forgot I'm not teaching class, I'm making videos. So yeah, leave a question down below though. Yeah. Anyway, so that's it. So that's number 7. And now we are going to look at number 8. The truth is, the integral of square root tangent x is actually doable. It has the answer. This one does not, right? As I told you guys earlier. Now, we are going to come here and do a u sub first. Here we go, right? So let me just start right here. I will just actually just write it down again. So integral of square root of tangent x dx. Here we go. Let u equal to the whole thing, square root of tangent x. And let's get the x by itself and then differentiate. It's easier. Square both sides, so we get u squared equals tangent x, and take the inverse tangent on both sides, so we get x equals inverse tangent of u squared. And now we will differentiate both sides, so you will see that this is not integral, just an arrow. Dx equals, the derivative of this is first 1 over 1 plus this thing square. So we have u squared here and then square. Right, this thing square. And the chain rule says we have to multiply by the derivative inside. And that will give us 2u right here. And of course, this is still with du. Now, we put this back here. Check this out. Here we go. This is going to give us, of course, square root of tangent u. Square root of tangent x is the u. So we have the integral u dx is all this. So let me just multiply by 2u over 1 plus. This is u to the 4th power. And we are in the u world. That's great. Of course, we can just multiply the u's. So this is just integral of 2u squared over 1 plus u to the 4th power du. Now, here is the idea. We do have a rational function, meaning a polynomial over a polynomial. We have a really good chance to integrate that. But sometimes it can be really, really hard because the procedure is pretty long. Yeah, just like this one. It's actually pretty bad. Well, it's not that bad if you get used to it. So now, this is what we are going to do, right? So just kind of, just kind of calm down a little bit. First of all, we see the 2u squared over 1 plus u to the 4th power. It would be nice. You will see why it's nice. It would be nice if we have the powers being slightly more balanced in the denominator. When we have the u to the 4th power and then plus 1, let's just have the following, okay? I'm going to divide everybody by u squared. Divide everybody by u squared. Divide everybody by u squared. And when we do that, we end up with the integral. On the top is just 2. And the bottom, let me actually write this down first. Why not? This is going to be u. Okay, this one right here goes first, okay? U squared. And then this right here is plus 1 over u to the 2nd power, right? So, yeah. Okay, I know, I don't usually do that, but let me just put that down first, okay? Anyway, now we have no variables on the top. We have just u squared plus 1 over u squared. In fact, we can complete the square right here. Let me show you how. Let's put it down here. Yeah. So have a look here. When we have u squared plus 1 over u squared, well, this is the sum of 2 squares. I'm not going to do trig sub. I will just complete the square. And this is, of course, not factorable. I'm not going to use complex numbers, but this is how we can do it. Check this out. This right here, I will put it down as parentheses, something square, and then plus 2 something, and then something else, and plus something square. On the left-hand side, we have u square. So perhaps the first parentheses, I'll just have the u. And this right here is 1 over u square. So perhaps I could have written this as this to the second power. So 1 over u can go right here. And this is just u, that's 1 over u. That's good. And when you look at this, u and 1 over u, they cancel, so we are just putting down plus 2. Right? On the left-hand side, this is what we have. On the right-hand side, this is the same as that, this is the same as that, but we have an extra 2. It's okay, because we can just subtract the 2. That's minus the 2 right here at the end. And that will be very nice. Well, have a look. Here, the first 3 terms preferred it because we can factor it and it's a perfect square, and we'll end up with u, and this is plus 1 over u, and then square, and of course we have the minus 2 at the end like this. So that's good. And you might be wondering, why didn't I minus the 2 first? The truth is, we can have done so as well. So if we repeat the same procedure real fast, we see that u square plus parentheses 1 over u square, we could have done this. Parentheses square minus 2 parentheses plus parentheses square. And this is preferred, right, to factor. And you see we can put a u here, 1 over u here, u 1 over u, and this right here will be the minus 2. And we can just add the 2 after that. So that's good. And the idea is, you see, the first 3 terms right here, they will give us u minus, because of the minus, 1 over u square. And then we have the plus 2, like that. So this is good. We can factor it, but which one to use? The truth is we use both. Now, here is the deal. We can replace this down in the denominator, or this down in the denominator, right? But the problem is that on the top, it's just a number. It's not that good. We wish to have the derivative of something. Check this out. Well, here I'm just going to pick another variable to equal to this. So I will just say that t equal to u plus 1 over u. And let's do the derivative. We will get dt being equal to 1. And the derivative 1 over u is minus 1 over u squared. And of course, we have the du. And this is actually really nice. And let's do the same thing right here. But here, I will pick another variable, let's say w. W equal to this, which is u minus 1 over u, and get dw. dw will be 1, and the derivative of negative 1 over u is plus 1 over u squared, du, like this. And you will see why this right here is really, really nice. Now, we'll go back here. We're going to somehow change this right here. Have a look. On the top, we have 2. Everybody knows 1 plus 1 is 2, but I know 2 is the same as 1 plus 1. So let's break this down. This is the integral. On the top, we have 1 plus 1. And you see that we do have the 1 plus 1 here. Well, if we can have this right here, that would be so nice. So let me make that happen. Minus 1 over u squared. In the meantime, that's also plus 1 over u squared right here. And down below, of course, we have this. But this is going to be so nice. You are going to see this real quick. Here's the deal. I'm going to do this over that, and then this over that. But remember, this right here as the denominator, we have 2 forms for it, right? Very nice. So here we go. On the top, again, this is just the same as that. But again, we are going to just kind of split it in a nice way. We will have the following. Well, we will have the integral. And I will have this on the top, which is 1 minus 1 over u squared over. I don't want to look at this anymore. I will actually look at this version right here. So let me put down this right here for you guys, namely parentheses u plus 1 over u square and then minus 2, like this, right? And this is still du. And we are going to close that, that's why I put on du. Next, we have another integral. I'm going to do this over that. On the top, we have 1 plus 1 over u square over this. Well, we want this. We want to look at this, right? So another look. So I will put down parentheses u minus 1 over u square and then plus 2 du, like that. Very nice. Now, after the substitution, now we have put down right here. For the first one, we use t. For the second one, we use w. For the first one, you see, this right here is t. On the top, that's precisely our dt. So we end up with this integral. Again, all this right here is the dt. Meanwhile, this is the t. No, we did that. Very nice, right? So this is going to be the integral of 1 over t squared minus 2, and then we have dt in green. Why not? It should be actually dt. And then for the second one, we add, well, this part, 1 plus 1 over u squared, is dw. W is that, right? So this is the dw part, and this right here is the w, not omega, okay? This is w. So for the second one, we have the integral, and this is going to be 1 over w squared plus 2, and we have the dw right here. Man, it's a lot of work. I know. Guess what though? More are coming, right? More and more are coming. It depends. It depends how you want to do it actually. It's actually not that bad because in fact I will use some hyperbolic function to finish this. I think I will just do that. This right here is going to be some kind of inverse tangent because of the sum, and this right here is a difference, so we can use hyperbolic function for it. Well, let me just use that, yeah, because it's been a while for this question already. Okay, so let me just remind you guys some formulas. Let's see, put it down here, okay? When we have the integral of 1 over, let's say variable, which other variable that we haven't used here? Oh my god, d, v, x, y, z, I don't know. Let's just put down, well, man, I cannot run out variables already. I don't want to use y and z, that's too... Okay, I will just use y squared plus a squared dy, okay? This right here, in fact, we have a nice way to do it. It's just 1 over a, and then the inverse tangent of y over a, right? And then plus c, of course, but I'm not going to write that down. And the other one is 1 over y squared minus a squared dy. Well, you can use the inverse hyperbolic cotangent or the inverse hyperbolic tangent. Either you put down 1 over a, but in fact, this is going to be a minus. Because technically, if you look at the derivative, it's the other way around, but just trust me, it's a minus. You can use either the inverse hyperbolic tangent, the one with h, y over a, like this, or you can also use negative 1 over a, the inverse hyperbolic cotangent of y over a. And you can also use the natural log by doing some partial fractions, but I think I'm so done with this question, so let me just finish that, okay? The truth is, you should use this one. You should use this one. Depends on the input, but let me just tell you, we should use this one. Anyway, let's just finish this question, okay? So, let's come back here. This is going to be, for this one, we have the inverse. And it depends on the domain, so that's why I say that, okay? So, here we go. We have negative 1 over a. So we have negative 1 over, well, look at the 2 as the square root of 2 over 2, of course, just like how we did it earlier with some of the questions. So we look at it like this. So we have negative 1 over square root of 2. And the inverse hyperbolic cotangent, like this, right? Input, because the input is like greater than 1 or like less than 1, you have to choose differently. But again, I'm not going to worry too much. Here we just have the t as our variable, so we have the t, and we put it down. So we have t over that. So it's t is just t. Man, t is what though? Let's do that later. T over a, which is square root of 2. So we have t over square root of 2. Like this. Yeah, so this one give you that, right? And similarly, we do this one, which is for the inverse tangent, which is for this one. So we have plus 1 over, and again, we will look at the 2 as the square root of 2. Square, that's how we can get that 2. That would be good. So we have 1 over square root of 2, like this. And this is the regular inverse tangent. So let's put that down right here. And the variable that we're using is w, and over the square root of 2, like this. Whew. And we're done with the integrals, right? But now we have to get back to the x world. So now, let's see. And I'll just put down this in black and green, like why not? Okay, so here, negative 1 over square root of 2. Negative 1 over square root of 2. Yeah? And we have the inverse hyperbolic cotangent. And t is, man, is u plus 1 over u, and u is what? U is square root of tangent x. So just keep that in mind. This right here is the square root of tangent x. So let's put that down. And perhaps let's write it down as 1 over square root of 2 times t, which is the square root of tangent x. Let's put that down, square root of tangent x. Right? Square root of tangent x. Not tax. Come on. I'm not paying the tax yet, right? Yeah, it's not a tax season yet. And then 1 over u, which is 1 over square root of tangent x, and that's going to be cotangent in the square root, right? So this is going to be plus square root of regular cotangent x. Yeah. And if you haven't covered the inverse hyperbolic cotangent, you can just check out my other videos, see how to integrate this guy, but I will leave that to you. And for this part, we add 1 over square root of 2. Let me just put on this in black. And the tangent, and the w is the minus version. And again, we have the 1 over square root of 2. Parentheses, we have the square root of tangent x. And we are going to minus 1 over 1 over u, which is that. Well, cotangent inside. Okay. All right, so this right here is the answer. In fact, I have a video on just this question, but I think I should have used inverse hyperbolic cotangent in that video. But nobody complained, so we all good. Yeah. Anyway, seriously, look at this. Took a while. So look at this. Now, ASMR time. Here we go. Okay, I'm back. All right, so now continue with number 9. Just 2 more to go. It's not that bad. Okay, one of my favorite one actually, number 9. The integral of inverse tangent. Oh, we used the inverse tangent of x here. Okay, versus the other one, the inverse sine on the top over inverse cosine on the bottom. like this. Of course, we're talking about integral. So have a look right here. Which one is not doable? Or which one can we do? Can we do this? Well, let's give it a try. The answer is not 1 over 1 plus x squared. That's the derivative. We are talking about the integral. But knowing the derivative will certainly help. Because right here, we can try to do integration by parts. So here we go. I'm going to put down d and then the I. And plus minus. We are going to differentiate inverse tangent of x first. And then integrate 1. Differentiating this, we get 1 over 1 plus x squared. Integrating 1, we get x. That's good. Now, this times this is the first part of the answer. So we get x times inverse tangent of x. And don't forget, multiply the second row. And this is still going to be an integral. And this is the minus integral. And we have x over that. X over 1 plus x squared dx, like this. And this is actually totally doable because we can just do a u sub for this. And let's just put it down right here. That u equal to 1 plus x squared du will be 2x dx. Divide the 2x on both sides, we get dx equals du over 2x. Now this integral will be the integral. On the top is x over the bottom, which is the u. And dx is du over 2x. And x cancel, so we are just integrating 1/2 and 1 over u du. And this is going to give us a natural log. So this is good. This is 1 over 2 natural log. U is that 1 plus x squared. And this is always positive, so we don't need the absolute value anymore. Parentheses is enough. So this part is for this little integral. All in all, to answer that, we will just go back here and write this down in black, of course. Let me just see. Here, we get the answer. X inverse tangent, x. And this integral is this, and that's a minus in between. So we have the minus, right? Keep in mind the minus. 1/2 natural log, parentheses, with 1 plus x squared, like this inside. Put a plus c. This is it, right? But is the inverse tangent x the same as inverse sine over inverse cosine? And we were able to do this, and then shouldn't this right here just be the same answer? We know tangent is equal to sine over cosine, so inverse tangent is the same as inverse sine over inverse cosine. That's not true. That's not true. That's not true, right? So here is the notation issue, okay? Whenever we are talking about the inverse trig functions, like this, for example, this right here, another notation is the arc tangent x. And again, this right here is the inverse, right? This is the inverse tangent, right? Inverse tangent. What that means is that if today you have, let's say, theta is equal to inverse tangent of x, like this. Well, you can take the original tangent on both sides, and the original and the inverse will cancel out. So this right here will tell you x is equal to tangent, well, let's put it down in the same order. Tangent theta is equal to x. So that's the connection. You just apply the function. You don't divide. You don't do anything like that, okay? Well, let me also tell you guys this right here. When we have inverse tangent of x, this right here is of course not equal to the inverse sine of x over the inverse cosine of x. And perhaps the easiest way to see this is that, well, the domain for the inverse tangent is negative infinity to positive infinity. Meanwhile, for this, no, I don't think you can even put in 2 into x. So that's a quick way to see why they are not the same, right? Well, therefore, this right here is the one that has no answer. And let's use special function, which I'll do that for you guys in the future video. All right, so that's it. Looks really cool, but unfortunately, it's not true. Now, one more. They do look super similar, but you know one of them do not have the answer. Which one? This one doesn't have the answer. Well, again, the reason is because we can totally do this one. So let's make that happen. So here we go. Right here, look at the integral of 1 over 1 minus x squared. And this part-wise, 1 minus something squared, we can do a trig sum for that. And especially, we have to take this raised to another crazy power. This is the 3/2 power. Now, 1 minus something squared, we should use sine to help us out. So, I will take x equal to sine theta. And this is nice because this is just 1, so we don't have to multiply by a constant. Anyway, dx is equal to the derivative of this, which is cosine theta d theta. And now take this into the theta world. Here we go, integral, and we have 1 over, this is 1 minus sine square theta. And we raise this to the 3/2 power. So here we have the 3/2. And this time, we'll not forget, dx is cosine theta d theta. So let's put down cosine theta d theta right here. Now, 1 minus sine square theta is just nicely equal to cosine square theta, so that's very, very nice. So, inside, we have cosine square theta. However, don't forget, we still have to raise this to the 3/2 power. And of course, what's really nice is that this square and that half power, they cancel. So we just have cosine to the 3rd power in the denominator. So let me just put that down, cosine to the 3rd power theta. And we have this, namely cosine theta to the 1st power right here. And this is cosine to the 3rd power. So in the end, what we can do is cancel more things out. How wonderful. Cancel this. And finally, we just end up with 2 down here. And have a look. This is going to give us what? The integral 1 over cosine square theta, namely secant square theta d theta. And this is really easy to integrate because we know the derivative of what? Yes, regular tangent will give us secant, right? In the end, of course, we have to go back to the x world. Well, let's look at here. We know sine theta is equal to x. So we can look at this as sine theta as x over 1, because by looking at this, we can draw a right triangle. And let me just put a right triangle here. Theta here, right angle here. Sine is opposite over hypotenuse, and the adjacent here will be the square root of the hypotenuse square, which is 1 square here, minus the opposite square. And that's what we have. Tangent is just opposite over adjacent. So in the end, tangent theta, this is nicely equal to x over that. X over square root of 1 minus x squared, like this. And with that being done, we are done as well. Put on a plus e. This is it. It works out so nicely. Unfortunately, when we have 2 over 3 power here, this wouldn't work out nicely. You see, this was for this one. This one doesn't have the answer. Yeah, very, very, very nice. Alright, so this is it. Hopefully you guys all like this video. Leave a comment down below. Let me know which one was your favorite. And maybe you can also give some insight on how you can kind of spot which one is not doable, which one is actually doable. My recommendation is that know some famous ones that are not doable, such as if you have a square in the cube root, something like this, then that's not doable. Sine of x squared, etc., etc. They are not doable. Check out my other video for special functions if you like. And yeah, thank you guys so much for watching. And as always, that's it.